Let's go ahead and start off with writing down what the chemical equation is. So it's a single replacement reaction that we're doing with this. So what must you have in a single replacement reaction?
A reaction.
Great. What do you need in the reaction?
One to switch with the other.
What is it? What do you mean one thing to switch with another?
Where you're replacing one thing, right?
What do you mean by one thing? A dog?
One molecule, one atom.
That's two different things. So which one? Atom. So you have to have an element. Are we okay with that? And in this case, the element's going to be iron. So you have to have something by itself, and that something needs to be an element by itself. So in this case, we're going to have iron. So Fe solid. And then the other thing that's going to be in there is hydrobromic acid, so HBr. And the state for that? Aqueous. All right. And what's going to get replaced in the hydrobromic acid?
The H,
Why the H? Has to be the H, but why?
because it's positive.
It's positive. And it's a metal. And so what are your charge possibilities for any metal? Positive or not negative? Positive or, what's the charge on that iron right there that I've got written down? 0. So no charge, meaning it has exactly the same number of electrons and protons, or it can give some electrons away. But under no circumstances can it accept more electrons. So it cannot take the place of the bromine. You okay with that? It can't be the negative thing. So the thing in the binary compound, the hydrobromic acid, that's positively charged is the hydrogen. So that's the thing that's going to get bumped out. So can I just bump out an H? Are we good with that? Has to bump out as an H2, right? Because it's elemental hydrogen. So it's H2 and it's a gas. And then the iron and the bromine are going to go along with each other. So what's it going to make? Yeah, it'll be aqueous for sure because there's water there, and we know there's water there because there was water there with the hydrobromic acid. And we know it's soluble because bromines are soluble and there's no iron rule. But what's the formula going to be for the substance?
FeBr2.
Is it?
Iron bromide.
Is it 2? So take out the table. Find yourself some iron. Find yourself some oxidation states.
2, 3, or 6.
2, 3, or 6. And anything else? Look very carefully at 2, 3, or 6.
The 3 is
It's 3. It's 3. How do you know that? It doesn't have to be, but you were not given environmental conditions other than what you would just normally see. So under these circumstances, if you put these two things together, if we went next door and we could do this and put them in the lab, you'd end up with FeBr3 for sure. And yep, it would be aqueous. So unless something specifies telling you that the formula for the substance is going to be 2 charge on the iron or a 6 charge on the iron, it's going to be whichever one's bolded. Okay. So it sounds like most of you did FeBr2. So let's just go ahead and do that. Did anybody do Br3? Good job. Say again?
Is it 2 Fe3 Br3 or no? Oh, sorry. The 3, the by the Fe's is the 3 go in parentheses?
The 3 go in parentheses?
Yeah, you know how like, because of the charge, right? You said it has to be 3. The iron charge, do we put that? You put 2 Fe and then in parentheses the charge?
I'm sorry, did you do this?
Yes. Is that wrong?
That's wrong. What's that 3 for?
I thought that was to specify the charge of the iron.
And you do that in the name. That's where it belongs in the name. So we'll go with this. Iron, so what's the name of this? Iron 2 bromide. Okay, so we're gonna make ourselves some iron 2 bromide. I've been given 125 grams of iron and 275 grams of hydrobromic acid. Great. What?
Not balanced yet.
Yeah, good call. I need a 2 right here. I've been given 2 reactants, and those 2 reactants are going to react together. And when are they going to stop reacting? When, not when they both disappear, because they're not going to both disappear. One's going to run out. Why won't they both disappear? They're both not going to run out. Nope, absolutely not. The whole point of these questions is to figure out who runs out first. Great. Okay, so why don't they both run out?
Because we can't count individual atoms.
No. No.
There's more of one thing than the other.
There's more of one thing than the other. If you're making hot dogs and you've got 12 hot dog buns and you've got a pack of 8 hot dogs, how many hot dogs can you make? 8. And then what do you got? 4 leftover buns. So are you gonna run out of the hot dogs and the hot dog buns? You're not. And we're not gonna, one of these things you're not gonna run out of. In any reaction, it doesn't matter the number of reactants, what's gonna end up happening? One's gonna run out first, and all the rest of them you're gonna have left over. What you would like is to have maybe as few of the extras left over as possible. But if you're just grabbing some of this and grabbing some of this and reacting them together, one's going to run out first, and it doesn't really matter. What if I had, we're going to find out that the hydrobromic acid runs out first. Does it matter if I've got 10,000 pounds of iron or 125 grams of iron? No, the hydrobromic acid's going to run out first. It doesn't matter how much iron's there, just as long as there's enough iron to use all 275 grams of HBr. Okay, so how do I determine that the HBr is the thing that runs out first?
Maybe we'll have to do a Wilder trap for 1.5 grams of iron and 275 grams of
Okay, so I take this amount of iron, this 125 grams of iron, and react it and figure out how much hydrogen gas I'm going to make. Then I take my HBr and react it and figure out how much hydrogen gas I'm going to make. And whichever one is smaller, that tells me which one of those 2 is limiting reagent. Okay, let's go ahead and do that. So I've got 125 grams of iron, and so this is my mass of iron. Great. What do I need to do with my mass of iron? I need to figure out how many atoms of iron are there, right? And so I'll use my molar mass. And so 1 mole of iron has a mass of what?
55.845.
Okay. So what's this first conversion do for us?
Count your atoms.
It just counted how many irons I've got. Okay, so now I know how many irons I have. So I don't care about my number of irons. I want to know how many hydrogens I'm going to make. So what goes right here in the equation? Right here.
1 mole of iron.
Let's just go with the unit first off.
Mole.
Of.
Iron.
So I know mole of iron has to go here because mole of iron is up here and they need to cancel out. And I'm looking for hydrogen, so I'm going to put moles of hydrogen. So it's super important that you put moles of H2 there because there is no H present. So whatever you have in the balanced chemical equation, those are the only things you can use as unit classifications in your calculation. All right, so now that I've got this mole to mole ratio, I need to put a 1 in front of the iron and I need to put a 1 in front of the hydrogen. That's because the balanced chemical equation coefficient is a 1 for each of those. All right, so what did this next portion of my calculation do for me?
Gave you the ability to convert to hydrogen.
It can't stop
It-
You need the hydrogen for the next portion.
Okay, great, but what do I know right here? What did this just do? What did,
Should you your ratio for one coefficient?
okay,
That's your-
there we go. So this right here counted how many irons I have in 125 grams of iron, right? And if I had 125 grams of iron and I used it all up in a reaction, this right here tells me what?
how many hydrogen?
How many hydrogen gases I'm going to make. The actual physical number of hydrogen gases, which is kind of useless to me. Why? I can't count them. There's just too many of them. But I can count them based off of their mass. So what has to go down here in the denominator?
Moles of hydrogen.
Moles of H2, and I'm going to want to know my grams of H2. So the number in front of this ratio for moles has always got to be 1, and then I just look on the periodic table for the mass of 2 hydrogens, and so it's, what, 2.59. All right, great. So what's this last step do for me? No, it doesn't count them. We already did that.
Gives you the mass.
It gives me the mass. So this part here counts my irons. This part here counts how many hydrogens I'm going to make. And then this part right here tells me the mass of those hydrogens. Okay. And so I've got grams of H2. And somebody got an answer for me? It's like 4 something or other?
4.51.
Okay. So 4.51. What did this question assume? What did this railroad track, this calculation assume?
Enough oxygen? Or not oxygen,
That was last week.
yeah.
That you had enough hydrobromic acid, right? This is saying I'm going to use all 125 grams of my iron, and if I did, I would make 4.51 grams of hydrogen gas. Fine. We don't know that you can actually do that yet. So what I need to do now is start off with my 275 grams of hydrobromic acid and figure out how much hydrogen I'm going to make. So I'll start off with 275 grams of HBr and 1 mole of HBr and then grams of HBr. So what's the gram number down here? It's like 80 something or other.
80.91195.
80.91195. That sounds great. Okay. So what did this first step do for me?
Counted your hydrobromic acid.
Counted how many hydrobromic acids I have in 275 grams of hydrobromic acid. What parameter am I gonna, what am I gonna put right down here in the denominator?
Mole of hydrobromic acid.
So mole, HBr. And what am I looking for?
Mole of H2.
I want to look for the exact same thing I was looking for before, otherwise it doesn't really work out for me. So my ratio is going to be what?
1 to 2.
And so the 1 came off the balanced chemical equation, and the 2 came off the balanced chemical equation. So what did this next portion do for me?
Count how many hydrogens you were going to make.
How many hydrogens I'm going to make if I use 275 grams of hydrobromic acid. Okay, and then I need to put moles of H2 here. That way I can cancel those out. And then it'll be 1 because it's going to be grams of H2. And then it'll be 2.0159. And so grams of H2. And the, somebody got a number here? Like 3.
3.43.
Great. Okay. First off, what did this assume?
That you had enough iron.
That you had enough iron. So the first one assumed I had enough of the hydrobromic acid. The next one's assuming I have enough of the iron. Which one of those assumptions was correct? The second one. We did not have enough hydrobromic acid. We had enough iron. So the moment that I've made 3.4 grams of hydrogen gas, what happens?
Your reaction stops
My reaction stops what?
because you ran out of hydrobromic acid.
There is 0 grams of hydrobromic acid left. So this question asked what is left in the container when the reaction is finished. So I can already make one answer. I can make 2 answers. What are my 2 answers?
Iron.
I can give you exact amounts of 2 things. What?
Hydrogen and your
I know that there are 3.43 grams of hydrogen gas in the container, for sure. What else do I know? No, I don't know the iron.
Or the hydrobromic acid.
I know there's 0 grams of hydrobromic acid because I just used it all up. So what I need to do is figure out how much leftover iron I'm going to have and how much of the iron 2 bromide that I made. Okay, so that means I'm going to need to do another railroad track, and I'm going to use my 275 grams of HBr. Why do I not need to do another railroad track with the iron?
Because
Because you don't know how much you're gonna use.
Sure,
It has too much.
I'm going to have leftover stuff, so it doesn't really matter if I calculate how much iron 2 bromide am I going to make, because I can't make that much. So you don't need to bother with another calculation. So when you're doing these, once you've assigned the limiting reagent to one of the reactants, then all the rest of your calculations go off of that. So my hydrobromic acid here, and then I'll put 1 mole HBr, and then I'll put 80.91195 grams of HBr, and then 2 moles of HBr, and 1 mole of iron 2 bromide. And then for every 1 mole of iron 2 bromide, I have grams of iron 2 bromide. We got a mass for the molar mass for the iron 2 bromide. 215.653. 653. Okay. Excellent. And so then this will give me grams of iron 2 bromide. And how much do I make? 366 grams. Okay, good. All right, so some stuff to consider here. I know 3 things now, right? I know how much hydrogen I'm making. I know how much iron 2 bromide I'm making. I know the fact that I have no more leftover hydrobromic acid, but I have some leftover iron. So there's 2 things we could do to figure this out. We could either do another railroad track, another calculation, starting with my hydrogen bromide, my HBr, and then calculate how much iron I would need, and then subtract that number off of the amount I started with. Or, since it's a simple problem, I started with, how much? 125? I started with 125 grams of iron and 275 grams of HBr. And so I got 400 grams of stuff to start with, right? I made 3.43 grams of hydrogen and 366 grams of iron 2 bromide. These 2 numbers here do not add up to 400. How come? Because there's leftover iron. So all I need to do is add these 2 numbers together, and then that'll be 369.43 grams of product, and then take that and subtract it from 400, and that'll tell me how much iron I have left over. So what does it work out to be? 41?
31, round.
31.57 grams of iron left over? So 31.6? Okay, so then the answer to this question is going to be this. Ooh, that's terrible. Let's go with this. Wait, what happened? There we go. That and that and that and 0 grams of hydrobromic acid. Sure. Thanks. Is that better? No, so then that's got to be a 6. There we go. Good? Can I say something about a lot of calculator work? I know, you can thank me later. So let's do the exact same thing with the next problem. Before we get started with doing the calculations for this next one, let's talk a little bit about this equation. So do you know states for some of these things up here? What do you know right off the bat? What should you know? You should know this one right here is a solid. This one's a solid because it's just carbon, and carbon's a solid on the periodic table. And this is chlorine gas because it's chlorine, and that's a gas on the periodic table. And then the last one? Yeah, it would be super awesome if we could write aqueous, but why in this particular case do I have to write a gas? Because there's no water anywhere. Yeah. And how do you know that these things can turn into a gas? Well, last week we did a lab with hydrochloric acid, 9 molar. Did anybody have irritated eyes? Yes? No? Nose irritated? Sniffly maybe? Okay, well, that hydrochloric acid was turning into a gas right there, and so it was hitting you. And those hydrochloric acid molecules were separating because they're aqueous inside of the mucous membranes and in the tears that you have, and so all of those things became a little bit more acidic. So under normal circumstances, I know I said acids are going to be aqueous, and that's usually the case. But if you can prove there's no water present, then okay. And how do you know that there's not going to be any water present? Well, let's go to that first thing in the problem. What is this first thing up here? It's the molecule decane. I don't care that you know the name of it, but what type of molecule is it? Type. Okay, hydrocarbon is a subtype for sure. What's the overall type? Is it ionic, covalent, or an acid? Is it ionic? It's definitely not ionic because two things. There's no metal and there's no polyatomic ions, so it's not ionic. Is it an acid? Doesn't start with an H, so it's not an acid. It is covalent then, right? So then you have to ask yourself, is that covalent molecule polar or nonpolar? Well, the quick way to do it is look at the electronegativities for the carbon and the hydrogen. They're not very far away from each other. It's less than 0.5. So then this is a covalent molecule, but it is definitely not polar. It can't be polar. So that means that this is a molecule that doesn't really like to, polar things are the things that are going to like to stick to each other, right? Does that make sense? So these are non-polar things, so they don't really like to stick to each other. So the chances of this being a solid are pretty slim. And we've talked about hydrocarbons before. What do you know about them? The bigger they are, the more likely they're going to be a liquid. The first three are gases, right? Methane, ethane, and propane are gases. Then the next one is butane, and that's right on the border. It's a liquid, but if you just put it into your hand's warm enough to turn it into a gas. And what other hydrocarbon do you know? Octane, gasoline. What state? Liquid, and this is bigger than that, so liquid. That's how you come to the fact that this guy here is a liquid. Or you could have Googled C10H16 and checked it out, and it would have shown you that it was a liquid at room temperature. And actually, this isn't decane. I just realized it says C16. It's unsaturated hydrocarbon. So there's double and triple bonds in this, but it's still going to be, I absolutely cannot, and nobody on this planet could tell you what molecule that is. There are double and or triple bonds in it, but nobody's really sure where, because it would be like me giving you 10 black Legos and 16 red Legos and saying, go. We're not all going to build the same things. So there's a lot of different possibilities with this molecule. But regardless, it's carbons and hydrogens, more than 8, so we're looking at a liquid. Great. So I burn this thing, I come up with those things. So it's 125 and 275 again? Okay. And then what do we, so how are we going to approach it? What are we going to do first? Balance it? Okay. Excellent. So what do we need to do? We need 10 carbons here. That looks good. All balanced up. So to answer the what's left in the container question, how are we going to start it?
25 grams of C10H16.
Sure. 125 grams of C10H16.
Is there a way to do it that's easier than the other, or does it really matter?
What?
If you chose to do the chlorine instead of the other one, would it really?
You have to do them both.
I
Right?
mean, the carbon or the hydrochloric acid.
Oh, no, I'm sorry, the reactants.
Yeah.
So we have to use both of the reactants, but it doesn't matter which product you pick. So if it was me, I would pick carbon because I don't have to add anything up. Not that adding 1 and 35.5 are hard, but I can just look and get 12.011 off the table. So that's what I would do. But is there any other reason to do it other than it's quicker? No. So down here, I'm going to put grams of C10H16, 16, and then 1 mole C10H16. And then, do we have a mass for that? 236. Okay. So again, what's this first step do for us? It counts how many of the C10H16s we've got already. And so I'm going to put mole C10H16 and mole, I'm going to put carbon since that one's easier. And I'll put a 10 here and a 1 there. Are we okay with the 10-to-1 ratio that I've got written down? And then I'm going to put moles of carbon 1 and then 12.011 grams of carbon. And already? Somebody got a value there?
110. What I rounded it to.
110
Yeah.
with a decimal place? 3 sig figs? Is everybody okay with 110? No? We can knock it out. So I got 125 times 10 times 12.011 divided by 136.236. I got 110.185, so good job, rating. Great, so if I had 125 grams of C10H16 and what?
Enough chlorine.
And as much chlorine gas as I would need, I would make 110 grams of carbon. Awesome. So now what do I need to do?
Do the chlorine and carbon.
Now I need to figure out if I have enough of the chlorine. So I've got 275 grams of the Cl2. And so then I'll put grams of Cl2 and 1 mole Cl2. And then it's what, 70.9, what'd you say, 86?
906.
906, okay. And so this just counted my number of chlorines. And so now I'm going to figure out how many, if I had this many chlorines, how many carbons I can make. And it's a 10 to 8 ratio. And then moles of carbon to 12.011 grams of carbon. And then that's grams of carbon. So 275 times 10 times 12.011 divided by 8 divided by 70.906. And I got 58.2. Okay. So, what did we just learn?
The chlorine is your limiting reagent.
The chlorine is my limiting reagent. So in my container, there'll be 0 grams of chlorine when this is finished. What else do I know? There will be 58.2 grams of carbon in my container. So what do I do next?
Now you do chlorine and hydrochloric acid.
I do chlorine and figure out how much hydrochloric acid I'm going to create from that. So this next calculation is gonna look very similar to the previous one. I can just put in my 275 grams, just like I had above, and then my 1 mole, just like I had above, and my 70.906, and then my 8 mole Cl2. So to this point, everything's going to be identical as to the calculation where we determined it was the limiting reagent. Now I need to switch over to a different substance, and it'll be the hydrochloric acid. So it'll be 16 mole HCl. And so then I'll go moles HCl, 1, and then grams HCl. Somebody got a mass for that one?
6.461.
Great. Alrighty. $283. We good with that? Okay. So that just calculated how much hydrochloric acid is going to be in my container when I'm finished. So I got 0 grams of chlorine gas, 58.2 grams of carbon, and 238 grams of hydrochloric acid. I could do 2 things. What are the 2 things I could do now?
Another railroad.
I could do another identical railroad to the last 2, with the exception of me putting in the amount of C10H16, or I could say that I started with 400 grams, and I got to end with 400 grams. And so I've got 283, and I've got 58.2, so 2, 1, 4, 3. So that means my C10H16 is 58.8 grams of that left. Are we good with that? So that was just this subtracted off of my starting amount. So if I put 400 grams in the container, I got to have 400 grams total of reactant product remaining.